Hello everyone and welcome to the first tutorial, which is modelling the flow through a pipe. So first of all, what I'm going to do is I'm going to hold the left mouse button down on the CFX module here, the fluid flow module with the brackets CFX. Hold the left mouse button down and drag into the project schematic and release. So what we have here is all the tools necessary to perform a simulation in Ansys CFX. So anywhere from setting up the geometry, creating the mesh, applying boundary conditions, setting numerical methods, and solving and post-processing your data. When we first bring this module in, we have the option of changing its name, and it's highlighted at the bottom here in blue. So I'm going to change the name here to pipe or pipe flow. And if I just press enter, that name will save. So the first thing we need to do is create some geometry before we can go on to build a simulation or set up a simulation to model the fluid flow through a pipe. So the first thing to do is right click on the geometry, and we have several options here on how to build our geometry. We have space claim, or we have design modeler. I'm going to use design modeler in this instance, as it's one of the most used and simple methods for creating relatively simple geometry. So when you're comfortable, left mouse click and wait for it to load. If you look in the bottom left hand corner, there is a bit that says starting design modeler. So if you're ever wondering whether or not your program is starting, it's always visible in the bottom left. So this is the layout for design modeler. Like all Ansys products, there's going to be a collection of items in the left-hand tree. We're going to work on different planes, the X, Y, the ZX and the YZ. We're going to be creating a body, and that's going to be a body of the fluid. So when creating fluid flow simulations, I like to use the X direction as my longitudinal, or the direction that the fluid flow is most travelling in. So in this instance, that means I'm going to draw a circle on top of the YZ plane, and that's going to be my horizontal and vertical axes. So Ansys has this wonderful ability here. If you click on the X-axis here, it will rotate the X-axis to be facing you. If you scroll with your mouse button, if you scroll forwards, you will zoom in, and if you scroll backwards, you will zoom out. I want my pipe to be about 0.3 meters wide, just some arbitrary value, and I'm going to have it about 2 meters long. So when we sketch in Design Modeler, we sketch onto a plane, or we offset a plane, and then we sketch on that. So in this instance, I'm sketching in Y, and I'm sketching in Z. So if I select the appropriate plane here, left mouse button, we get these sketching options, and I want to create a sketch. So if I just hold there, that option says new sketch. So I'm going to click to have a sketch in the Y and Z directions. Now I'm going to left click on sketch, and an option has appeared at the bottom here, which is sketching. So if I click on sketching, I have the options to do some drawing. I have the options to modify the drawing, apply dimensions, apply constraints, and add some of the settings. I'm initially just going to create a circle because I want a circular pipe. So left click circle. And now I can choose where to create that circle. For simple post-processing later on, I'm going to create the circle with the center at the origin. So if I hover my cursor on top of this axis here, you can see a C forming. That C means coincident. So it means if I make my circle there, or the center of my circle there, it will be coincident with the Z axis. What I really want is my center to be coincident with the origin point. So if you see here, you can just about make out a P shape where the cursor is, and that means that my cursor, or center of my circle, is going to be coincident to the origin. I've already stated that I want the diameter to be approximately 30 centimeters or 0.3 meters. So I'm going to use this bar at the bottom to approximate how big I want it to be. So press my left mouse button for a second time, and that size, that shape is now made. Next thing to do is give it an actual dimension. So left mouse button, click on dimension, select diameter, and if you hover over the circle highlights, left click, it will select, then you can drag, and then left click again, and it will provide you with some dimension. But here it doesn't tell you what that dimension is. So if you don't know what a dimension is, or you don't know some value of something, you can go to Details View here in the bottom left, Details View tab, click on it, and here you go. The dimension I've made, diameter 1, is available here. So I'm just going to change that to 0.3 meters. I'm using the base units here because that's what makes most sense for me, but you can also change to centimeters, millimeters, or feet, depending on where you are in the world and what application you're using. So I'm comfortable now that I've got a sketch and it's of a circle. So I'm going to click on Sketching Toolboxes, and then I'm going to go back to Modelling. So now if I hold down my middle mouse button, I can rotate, and I can see that circle is definitely on the YZ plane. I'm just going to zoom out a little bit. What I want to do now is go from having a two-dimensional sketch to a three-dimensional shape. I'm going to click on Sketch, and then I'm going to click on Extrude, and that's going to take me from having a circle to a circular cylinder. If I click on Extrude, and then go down to Details View, because there's some details that haven't been clarified, for example, which direction and how far am I going. I already had Sketch selected, and there's only one piece of geometry in this case anyway, so the software has automatically assumed that Sketch 1 is going to be my extruding geometry. It's assumed the direction vector to be normal, so we were sketching in the Y and Z directions, or the YZ plane, so the normal to that would naturally be X. So the software has taken that as default. There are other options, for example, you can go in different dimensions, you can go in one direction more than the other, but I'm just going to stick with normal for now. I'm going to make this a 2 meter long extrusion, so you can really see the pressure difference as we move along the pipe. So if you see here, this is the extrude creation, so this is the thing we were just making, the extrude. If we jump back to model tree, you can also see this lightning bolt symbol here. When you create something in Design Modeler, you will need to click this generate tool, or generate option, and that says you've set up your extrude. Now if you click generate, it will actually make it. So now I have this three-dimensional shape. What I'm going to do next, and it's not strictly necessary but it is good practice, is to begin naming different sections of it. So what I want here, just take a look at my Z-axis. I'm going to just hold down the right mouse button and drag a box zoom to see slightly better. But I want fluid to come in from this end of the pipe, I want it to move along, and I want it to leave at this end of the pipe. Therefore, I'm going to say to the software that this is going to be called the inlet part, this is going to be the wall, and then this circle at the end is going to be the outlet part. So if I tell the software that I want to select surfaces, so the face selection tool, left mouse button click on the inlet, right click, and create what we call named selection. So in this instance, we're going to select name selection and go to the details view. So we've already selected our geometry. I just want to change the name here. So I'm going to call it inlet, where the flow is going to come in. and we don't want to do anything else. We want to leave everything as default. And again, we're seeing this lightning bolt. So if you just click generate there and go back to the original tree outline, what you see is that name selection option with Inlet. I'm going to repeat that process. So I'm going to select the sidewall with my left mouse button. Then I'm going to right mouse button click, and I'm going to click name selection again. I'm going to go to details view, and I'm going to say call this wall. Geometry, that face is already selected, it's already been highlighted green. I'm going to click apply, and again we've got this option here to use the generate tool. So once I click generate, that action is now locked in. What you will see, if you go to details view, once you click generate, and this is just for the inlet part, you get this grayed out box here where you originally had the geometry selected. So now I can't change that unless I was to delete the name selection. Finally, I'm going to click, so I'm going to rotate first, click on the outlet with my left mouse button, then right click, select a name selection, go to details view, call it outlet. That geometry didn't just take. I'm going to make sure I've got faces selected, make sure that's depressed, left mouse button click and apply. One last time, click generate. And for this case, that's all we need to do. Got our parts, got our 3 different surfaces that we need. So now when you're ready, you can save the project, so make sure you do save these regularly, otherwise you'll lose all of your things. So I've just clicked save project. You don't need to do that, but I think it's good practice. Close this down and then move on to the next step. So next step in our CFD process is to generate a mesh. So if you double click on mesh, the default here is Ansys Meshing. So what we're going to do is create what we'd call a default mesh, the basic thing that the software will give us with all the basic settings. We're going to run a simulation with that and then compare the results of the basic settings to what happens when you refine the flow slightly better, you refine the settings better. Just going to expand that box there, that cross box, so you can see the menu, and just rotating around my shape. So we have the inlet predefined, with the wall predefined, and with the outlet predefined. I'm going to select the meshing option here, and it's already got this option to generate even though we've put no settings in. So what that means is that Ansys has these preloaded settings, and this is what it will give us as our mesh. So that's quite a coarse mesh overall. If we click down here on statistics, we can find out how many parts there are, or how many cells and elements. So there's approximately 3,000 elements. That's relatively small for a 2 meter case. You can also see that the mesh, if we zoom in, it's not very well refined close to the wall, so we're not going to be able to capture those flow gradients. But like I said before, let's see what happens with the default mesh, then let's see what happens if we do it properly. So we don't even need to save, all the settings are saved for us when we close. So now I'm just going to update the project, and then we're going to move on to the next step. So in the setup stage, what we're looking at is applying the numerical conditions for what we want to do, and applying the boundary conditions as well. So things like, how fast is our flow coming in? What's the boundary condition at the exit? What type of wall do we have? How does the flow behave close to the wall? Is it a smooth wall or is it a rough wall? Okay. So that's just got a little bit upset because it says we've not given any settings for CFX, which is quite correct. As ever, the solver is quite correct. And in the bottom left here, it said that we're starting. So welcome to the interface with CFX. So what we're going to do is move from the top of the model tree and work our way down. So the first setting of any consequence for us is this analysis type. So what this basically says is what type of analysis we're doing. So if we open up this option here, we have a steady state analysis. So we're using time average flow and RAND simulations. We have a transient simulation. So that would be if we were studying something that varies with time. So this could be a very turbulent flow, or this could be something that accelerates where time is absolutely essential. And we have the option for transient blade rows if we want to do some flow. Okay. So when you're happy with that, just OK. We're going to consider a steady state case now. So this option of default domain here, this is the domain that we're working with. So this is all of the geometry we just imported because everything we're doing sits within that domain. I'm going to leave this with its name of default domain and then double click on it. Here we have all the options for the nature of the fluid we're considering. So in this instance, domain type is a fluid domain. It works with a default coordinate system. And we've just got some reserve name here for our fluid. It's just fluid 1. And what I want to do is consider in this case water. So clicking on this drop down option, there are several default options: ideal gas of air, air at 25 degrees, or water. So I'm going to select water. It's continuous fluid, and because it's an incompressible simulation, I want to consider, I'm going to look at a reference pressure of 1 atmosphere, but in reality, reference pressures don't matter with incompressible simulations. If we go to the next tab along from basic settings, this is fluid models. So we've got an isothermal case at 25 degrees Celsius. The next question is, do we need to consider turbulence? So if we have a look, if you know the Reynolds number, so this is the number that determines whether a flow is going to be laminar or turbulent. And plugging in values for the U, so is your inlet velocity, the diameter of the pipe, and the kinematic viscosity. So these are approximate values for kinematic viscosity, but if Reynolds number is greater than 2000, we generally say a flow is turbulent. In this case, it's many times, 30 times greater than turbulent. So we can be quite confident that this is going to be a turbulent flow. So in this instance, we are going to be required to model turbulence, and I'm going to use shear stress transport model because of its ability close to walls. Okay. From here, I'm just going to click OK and assume that all our fluid models are correctly set. Next thing we need to do is specify boundary conditions, and you can do this by right-clicking on default domain, clicking Insert and Boundary, or you may also notice that the symbol here for boundary is also up here as well. So a slightly quicker way would be to do that. Click at the top. I'm going to call it Inlet, because we're no longer naming the geometry, we're naming the actual boundary. So it's this inlet here. The software has already picked up on the name, on the fact that we use the name inlet for the geometry, and it's the boundary type, so it's already picked up on that, and it's already put inlet boundary in as the inlet surface in as the inlet boundary condition. In the boundary details tab, next one along, we specify a normal velocity, or we can specify a mass flow rate, or we can specify velocity with cylindrical or Cartesian coordinates, or we can specify total pressure or static pressure. In this instance, I'm going to specify normal speed of 2 meters per second, and I'm going to say it's got a medium turbulence intensity of about 5%. Again, there are many options for what you may want to do here, but it's very much case dependent. I'm going to take a relatively low turbulence value. So once I click OK, that inlet velocity has been specified, and the software tells you by giving you arrows to say that flow is coming in. Next thing to do, I'm going to create another boundary, and I'm going to call it outlet. So just left clicking on boundary here, call that outlet. So again, the software has already picked up on the fact that the flow can leave the domain, and the boundary type matches the name of the surface that we specified in the last piece of software. So clicking on boundary details, I'm going to specify relative pressure of 0 pascals. So it's a very standard outlet condition. We normally say 0 pressure outlet condition. And what that's basically saying is that there's no change in pressure across that domain interface. Or the reference pressure is 0 outside. In reality, that may not be true for this case, because we're going to have friction at the walls, which cause decreased pressure. But what this outlet condition does is it gives us a kind of blend value. So it gives us an approximate value of pressure rather than specifying it as exactly 0. So just clicking OK, you can now see that the flow is out of the domain. So the software tells us that. And there's one more final boundary left, which is the wall. So rather than creating another one, I'm just going to right click, rename, and call it wall. Double clicking, it's already picked up on some bit of geometry, but I can just specify it as the wall. I'm going to say a no slip wall, so we're going to have 0 velocity on the wall, and it's going to be smooth, there's not going to be any roughness included. So once I'm happy with that, just click OK. And now we have all of our boundary conditions properly set up. The next place to go is solver control. So this is where we specify the maximum number of iterations, the intensity of our numerical scheme. So do we have high resolution? Do we have upwind schemes? This is all specified here. For a case of this magnitude, we can actually leave these all as defaults. I think this is going to converge much less than 100 iterations because of the low mesh density and the sheer simplicity of the case. In academia, we generally aim for a residual target of 10 to the minus 5. In some industry applications, they aim for 10 to the minus 3. Very much depends on what you want to do. But I've just said here, let's go for a residual of 10 to the minus 5 because it is such a simple case. We don't need to change anything else here, so we can just click OK. And for a case of this simplicity, that's all ready to go. So out of good practice, I'm just going to click Save Project. But in reality, I can just close CFX and everything will be saved anyway. So the next step is the solution. So this is what CFX calls the solver manager. So this is where the solution process is performed. There's no real activity required by the user here. It's all the work of the solver. The user is here just to monitor really and just make sure everything's working. And what we will be asked is, do we want to specify it as double precision? Yes, we always want to specify as double precision. This gives us a more detailed calculation. So we basically work to an extra set of decimal places when we're doing these calculations. This is especially important for things like large eddy simulation when you're doing enormous cases which last several months. Rounding errors can become significant. Also, if you're doing a fairly large case, you may wish to specify a local parallel case. So I've got 4 processors on this computer, so I can run my case across that. But because it's a relatively small case, 3,000 cells, there's no point doing that, it would probably take longer. So I'm just going to start the run and we can monitor what happens. So on the right hand side you see everything that goes in the .out file. So it's just a record of whatever's happening. You see the iterations and you see the values of all the flow variables. That tells me that the run is completed normally, so I'm just going to OK that, and it will tell us different things. It will calculate maximum and minimum values for velocity, pressure, turbulence, kinetic energy and other things, and it's also calculated a value of Reynolds number. So in this instance it says we've got a Reynolds number of 1 times 10 to the 6, and that's similarly agreed with that calculation, the same order of magnitude. So I'm going to close this down and then have a look at the results. So I'm going to do some very simple post-processing. We're going to do some qualitative, so we're going to look at a colour plot. Then we're going to plot some quantitative data. We're going to plot the velocity profile across the domain. So just zooming in on the XY plane and clicking location. I want to create a plane. It doesn't need to be called anything special. And specifying it in the XY plane and specifying that Z is equal to 0. So earlier I was very cautious to have the centre of my circle at the origin. That means when I create this plane, it can just be at 0. And that'll put it directly at the centre of the pipe. If I click apply, it creates, and it's currently got a constant value of colour, but I can change that to be a flow variable, and I can pick from my fairly enormous list. So I have many things to choose from. I'm going to choose from velocity, and I'm going to choose from velocity U, so that'll be velocity in the X direction. And clicking apply. What we can see here is that the flow comes in at the speed we set, so about that 2 meters per second. Then there's some boundary layer formation, and the flow in the centre is slightly above the 2 meters per second because it's had to accelerate to maintain mass conservation. And another thing I think is quite interesting is actually if you show the mesh lines here, take this option on and just click apply, what you can see is that boundary layer really does act right into a fairly large cell. So we're saying we're going from having 0 meters per second here to 20 meters per second here in a very small distance. So actually that mesh is nowhere near fine enough to capture the resolution of the flow. So we're going to need to rerun the simulation. I'm just going to click Fit View here, so it'll center that case for me. In terms of the quantitative data, if you click on Location at the top, create a line, and I'm just going to create a line right at the middle, vertically. So it's asking me for 2 coordinates. So I want to create 1 coordinate point here, and 1 coordinate point here. I know that it's halfway along, so in the X direction it's 1 meter. In the Y direction it's going to be minus 15 centimeters, plus 15 centimeters, and in the Z direction it's going to be 0. So in the X direction, 1 and 1. Because I'm working in meters, it's going to be minus 0.15. Actually, that's 0.15. In this direction, it's going to be 0.15. We have 2 options. We either have a cut or we have a sample. Cut will take samples from the nodes or the cells, but because we might have more cells later on, that will give us a different number of samples. So what I want to do is keep this consistent. So I'm going to put in a number here, 50. It's going to be very much interpolating the data, but it will still allow me to have that consistency. So now I've got that line, that yellow line has popped up. If you use the chart tool at the top, just click on that. OK. And it's going to ask me, where do I want my data? So if we go to data series and location, say I want my data to come from that line that I created. In the X direction, I want the velocity in the X direction, and in this direction I want to have the Y coordinate or the Z coordinate. So basically what I'm going to do is produce a velocity profile that looks a bit like that. So in this instance I want to go Y, because that's the direction my line is moving. Sorry, in the X direction I want it to be velocity in the X direction, and then in Y that wants to be the Y coordinate. Clicking apply, what we have here is a very blocky velocity profile. So you can really tell that's not properly refined flow. If it was, you wouldn't expect to see such sharp angles in a fluid flow simulation, even of this simplicity. So what we can say is that that's probably not right. And we could really tell from the mesh that we really weren't capturing those relatively high flow gradients. So what I'm going to do is export this data, and I'm going to save it as my coarse mesh. So what we can do now is we can click export here and save a CSV file of the data, and I'm going to call it coarse mesh. Once you've done that, close down CFX Post, and because we're working in this workflow in Workbench, we only need to change the mesh, and we can click one button and it will perform the simulation and bring our results back up to where we originally were. So what we want to do, what the problem was with our case was the mesh was too coarse. So the next thing to do is refine the mesh. So double clicking on mesh to load up Ansys Mesher. And what we're going to do is create prism layer cells. So if you refer to the fundamental aspects of CFD, which is held in another section of the... So if you right click on mesh, click on insert and go down to inflation, just zoom out so we can see the whole case. So first of all we want to click on this yellow area here for geometry, and that's going to be a body. So that's basically saying the fluid domain here. I want this inflation layer to exist in that fluid domain. The next is the boundary. So the boundary we're interested in is this wall here. So we're going to have these cells growing out of those walls. I'm going to change the inflation option to be total thickness. So what I have there is some control. I have some control over how far these inflation layers extend into the domain. So I want them to be a maximum of 2 centimeters. So converting into meters, that's 0.02. There's going to be about 5 of them, and they're going to have a growth rate of about 1.2. Which seems reasonable. So what we can do is click Generate Mesh, and that will create our mesh for us. So if you can't see your mesh, just click on the mesh option here, and there you go. If we just right mouse button zoom, you can see that the cells are very close to the wall. You see that we're not properly capturing the geometry of this circle very well, because it is quite a coarse mesh case. We can create smaller cells. So if we go down to the maximum tet size, maximum tetrahedral size of being, I don't know, 1 centimeter, so 0.01, and if we also specify the maximum face size, 0.01, got to consider that this is 2 meters long, so that's going to be at least 200 cells in the X direction, not considering the fact that we need cells in the middle as well. So if we run that, it might be too coarse, sorry, it might be too fine, might give us too many cells. So if we maybe say 2 centimeters instead, because this is only an example case, you may find that you need to refine your mesh further to get a certain level of result. But for demonstration purposes, we'll keep this relatively coarse. And there you go. So we've got a decent level of refinement. And I'm just going to close this. Now we've got a mesh. And I'm going to click Update Project. So now what's going to happen, the meshing is going to update, setup's going to update, the solution's going to rerun, and then the results are going to be replotted. So I'll be right back when this is done. So we're now at the stage where the solution is being run, so we can right click on Solution and to display monitors, just to see what's going on. So you can see the results from my previous simulation. They converged here, and the current one is 30 iterations in. So it began here at about 50, it's currently about 80, so it's on track to converge in the next few seconds. It's converging at relatively the same rate. Also consider that it had the old solution as its input, so it actually did quite well. It's done very well so far, in fact. 37, 38, it should be converging before 45. So even quicker than last time. Again, we are going to a relatively high convergence criteria here, for 10 to the minus 5. This will not always be achievable with your cases, but where possible this is what you should be aiming for the most accurate results. So that solver run has finished. I'm just going to shut Solver Manager down, double click on results so we can have a little look at what we've produced. So again, you can see the mesh, much finer than the previous case. You can also see, if we zoom a lot in, that relatively low velocity, close to 0, really doesn't exist for very far away from the wall at all. Earlier on it existed much further out here, and that's again just because the flow wasn't very well refined. So we've done a good job there with that mesh. We could probably make it finer and move these outer cells closer to the wall. Just clicking on Fit View. Another thing we can do is go to Chart, double click on Chart, and what we're seeing again is completely different from what we saw earlier. So the velocity is above 2 meters per second, and again that's happening because the low speed flow here is influencing the continuity, so we need to maintain continuity, we need to have the flow accelerate in this middle of the domain. You can also visualize pressure here, so you can see pressure drop along the pipe as a result of friction between the wall and the fluid, which is something we'd expect to see. So just going back to our chart viewer, what we can do is export this data, and I'll plot it in an Excel file and we'll just talk briefly through it. So now I've plotted velocity against the vertical coordinate, which we chose as Y, and I've done this for the coarse mesh and fine mesh cases. So what you can see is that for the fine mesh, the velocity stays much lower until it moves only slightly far away from the wall, whereas with the coarse mesh, you see a very, very linear behaviour until a free stream value at about 5 centimeters away from the wall. So it really does show the massive difference in results that you can obtain just from poorly meshing your case. So I hope this has provided an example of how you should really spend the time. Proper resolution of the boundary layer really does hold the key to very, very accurate results. And that's all for this tutorial. If we move on next, we'll have a look at some heat transfer in the similar pipe.